this is a summary of what I want to teach you. You have to think globally, so you have to enumerate all possibilities, but you act locally, meaning at every step in every neighborhood, I have to follow the law. So this is how I think, how clouds solve Navier-Stokes equation. When I look at the clouds, I have a shape, it's changing in time, etc. Now, there is no supercomputer in the sky that takes a billion points and runs it forward in time, a Navier-Stokes equation for the cloud, and gives me the solution. That's not how it works. The way it works is that in every neighborhood, the molecule looks to its neighbor, left, right, up and down, and says, look, we have to preserve total mass, we have to preserve momentum, we have to satisfy conservation laws. And, if I move with respect to you, you're rubbing me the wrong way, this calls it the Reynolds number. I have to satisfy this locally. And then as things rearrange themselves in time, everybody rearranges a little bit by solving the local equation. And that's how clouds solve Navier-Stokes equation. And that's how we should be solving all equations. We should follow the advice of the nature. And how does that work? We can only do it finite, but we can, extrapolate to infinity, because that's how we solve problems. We solve them finitely and then go forward. Every solution is a global fixed point equation saying that every little neighborhood, which is this phi, this field, every little neighborhood has followed Feynman law, which means there is a function of this neighborhood's whose sum equals 0. I put everybody on the left-hand side, I think 0. And every solution has global stability. If I perturb it a little bit, I will describe it by Hill matrix. And then there's a fundamental fact. This Hill matrix plays double role. One, it tells me how things respond to being perturbed a little bit every place, everybody in every neighborhood, every volume. But then there's this fundamental fact. It says that the volume of this matrix actually counts how many orbits are, because the volume of the matrix defines the size of the neighborhood, and the whole world has to be split into neighborhoods. There should be a sum rule, and that's the number of neighborhoods. And all of this information can be put into zeta function. And zeta function is what we call partition function in statistical mechanics. It contains all information. And as we have learned in our probability lectures in the last 2 weeks, it can compute all the moments. It can compute everything. It can give me any prediction on this system. The zeta function is the answer.
Okay, think globally, act locally. So what's our problem? Our problem is to enumerate and determine all global solutions of the Bernoulli system. And here is it stripped down to essentials. Each solution is a global fixed point. It's a zero of the function that implements the global satisfaction or demand for the law of motion to be satisfied. To be able to solve this problem, we have to understand global stability, which is the matrix of first derivatives of the fixed point condition, stability of that fixed point, and the variation of the field any place along the global lattice state. So this is a large matrix. The Hill global orbit. And then there comes the fundamental fact, which is the number of period end states is actually, for Bernoulli problem, it's the volume of, or the Hill determinant of the global stability. In this way, you can count how many solutions you have for each period little n, And once you know how many there are, you can also determine them from a fixed point condition because they're all the points that map from the parallelepiped into integers, the integer lattice within that volume, integer points in that volume. And if you know how to sum them to all order in a generating function, this generating function is called zeta function or topological zeta functions, you have totally solved the problem. Congratulations.
That's it. So now you know everything about physics. This math method course taught you almost everything there is to know, including chaos. And you're the only people who know it this way because everybody else is stuck in Newton's century where time marches forward. This is a modern view which unifies chaos with statistical mechanics and quantum field theory. Think of them all in the same way as in terms of quantum field theory. This is called path integrals. But in statistical mechanics, this is called partition functions.